Hello, everyone. I'm glad you are interested in our work. I'm excited to present our work, DS-NeRV, Implicit Neural Video Representation with Decomposed Static and Dynamic Codes. Implicit neural representation is a novel method that has emerged in recent years to parameterize various signals. It represents an object as a function approximated by a neural network that maps coordinates to their corresponding values. INR-based video representation, INR-V, stores videos as neural networks, inputs corresponding frame coordinates, pixel coordinates, and outputs corresponding signal values. In this article, we propose a novel video INR. Our work is based on the following findings. Typically, videos are composed of static elements that do not change over time and dynamic elements that change over time. As shown on the page, the grass and rocks in the background change very little between the three frames, while the bunny's pose shows noticeable changes. Therefore, in order to reduce the size of video INR, it is advantageous to compress these redundant, static information. On the other hand, dynamic elements need to be modeled smoothly throughout the video to preserve high-frequency details. In order to achieve this purpose, we proposed two effective designs. First, we designed a static and dynamic code to capture the static and dynamic information in the video. We also designed a fusion decoder to fuse the obtained static and dynamic information. We decomposed the video into static codes evenly distributed over the video timeline with a low sampling rate and dynamic codes with a higher sampling rate. The entire model only relies on RGB's L2 loss during optimization. When sampling static codes, we first obtain the two adjacent static codes indices Y and J, and then calculate their corresponding weights WY and WJ according to their distances to T based on weights and indices. We then perform a weighted sum to obtain the final static code. In this way, the associated static content can be computed for each frame index, effectively sharing static information throughout the video. Additionally, the sparse codes design also helps compress redundant static information. Different from the sampling method used in the static codes, we obtain the corresponding dynamic code CD through the interpolated dynamic codes CD up. The interpolation sampling method establishes global temporal coherence among dynamic codes through internal interaction, aligning with the perceptual continuity of motion in the real world. In addition, in order to effectively fuse the sampled static and dynamic code information, we designed a fusion module. During the fusion, the static and dynamic codes are first aligned to the spatial dimension through the initial upsampling block, and then the final information interaction and upsampling are performed through CCA fusion that implements cross-channel cross-attention. We then conduct extensive experiments on 3 datasets and various downstream tasks to validate the effectiveness of our method. Here are quantitative results on video reconstruction. And here are the quantitative results on video inpainting. Presented here are quantitative results of our method on video interpolation and video compression. We present here a video showing the qualitative results of all experiments. Detailed results can be found on our project homepage. Thanks for listening, and thank you again for your interest in our work.